Right, so this is a question on application of derivatives, and what we have is a cone. So let me draw a cone. So assume this is a cone, and it's filled with water initially, and at some point of time it develops a leak at the bottom. So what starts happening is water starts leaking from this tip over here, and it starts leaking at the rate of 5 centimeter cube per second. And what we are told is the base of the cone, which is the top surface, has a radius of let's call it capital R, 5 centimeters, and the height of the cone, which is measured from the base to the tip, so it would be this height over here. This is equal to, let's call it capital H, and it's equal to 10 centimeters. So the cone has some water, and the water is now leaking out of it. And the question is, how fast is the water level dropping when the water level is 2.5 centimeters from the top? So what does that mean? So let me just change colors, and let me show you where the water level is. So at any given point of time, the water level would be here somewhere, right? So let me just draw this. So let's assume this is the water level, and therefore what that means is this is all the water that's in the cone right now, and it's leaking out, so it's reducing all the time. And the question is, how fast is this water level falling when the water level is 2.5 centimeters from the top, right? So that's the problem. So how do we start thinking about this? Well, the most obvious thing to do is to take stock of all the things that we do know. So what do we know till now? Well, we know what the radius of the base of the cone is, which is capital R. We know what the height of the cone is, and we've been told at what rate is the cone losing water, which is dV by dt. So if V is the volume of water in the cone at any given point of time, so this is water in the cone, then we have been told what dV by dt is. And what we need to find out is actually how fast is this water level falling. So if I measure how far up the water level is from the tip of the cone, so what I mean is this height over here. So if this is how I measure the height of the cone from the tip, so if this is small h, then what we are being asked is what is dH by dt. So that's the question that we are supposed to answer. So let's see. So there's some things we know and some things we don't. So let's begin with the other more obvious thing that we do know. So how much water is there in the cone at any given point of time? Well, that's simple. This is the volume of this blue cone, which is equal to 1 by 3 pi r square h. Right? Now we know what h is. We don't know what r is. So what is r? Well, the r is just the radius of this cone of water. So let me very quickly just draw another line. So r is simply this radius over here, right? So let me just label a couple of points real quick. So let the tip be A, and let the center of the base be B, and this point over here, extremity, be C, and this point where the water level is, let it be X, and over here let it be Y. So r is simply equal to xy. This length over here. This is the radius of the cone of water at that point of time. So what we have is that. So that's what r is. And so this is okay. So this is the volume of water. And ideally what we would like is if we could form some sort of a connection between small r and small h, if we could find some relationship between them, then we could use that relationship to write r in terms of h. And we would therefore get this whole expression in terms of h. And that would be a nice thing to do, because what we are looking for is dH by dt. So we really want as much h in every value that we find. So if we can express everything in terms of h, then it will be easier to calculate dH by dt. So let's see if we can find some connection between r and h. So so let me submit this to you. Let's focus on this angle over here, right? Let's call this angle theta, right? So what is tan theta equal to? Well, if you look at the big triangle, which is ABC, so if you look at triangle ABC, then tan theta is simply the opposite side, which turns out to be BC, divided by the base, which turns out to be AB. Well, BC is just R, right? It's just capital R, and AB is just simply the height. So this turns out to be 5 centimeter by 10 centimeter, and it turns out to be half. But you will also notice that tan theta in the smaller triangle, which is AXY, in the smaller triangle, it's simply equal to opposite side, which is XY, divided by the height of the cone of water, which is AX, which is nothing more than R divided by H. Well, it's the same theta, so the tan theta is also going to be the same. So because this is equal to this, therefore R by H also has to be equal to half, which implies R is simply equal to H by 2, right? So this is great. We've now formed a connection between small r and small h, which means that we can now write we can change the expression for the volume of water in the cone at any given point of time to 1 by 3 pi h by 2 square times h, which turns out to be pi h cube by 12, right? So you can just check the calculation, but this is what it comes down to. So now we have an expression for the volume of water in the cone purely in terms of the small h that we had defined. And if we were to differentiate this, with respect to time, then it would be the same thing as differentiating pi h cube by 12 with respect to time, which turns out to be, well, because pi by 12 is constant, so I just take it out, d by dt of h cube, which turns out to be pi by 12 times 3h square times dh by dt. And I can just simplify this a little further, and this turns out to be pi h square by 4 dh by dt, right? So what we know is that dv by dt is equal to pi h square by 4 dh by dt. But we know what the numerical value for dv by dt is. So we know that dv by dt is equal to 5 centimeter cube per second. Well, strictly speaking, it should be minus 5 centimeter cube per second, because if V is the volume of water in the cone at any given point of time, then we know that the cone is actually losing water. It's not gaining water. So it should be minus 5 centimeter cube per second. So if you really want to be really precise, then just add the minus sign. And so dV by dt is minus 5 centimeter cube per second, which is also equal to this expression over here, right? So this expression over here, which is pi h square by 4 dh by dt, which implies that dh by dt, let me just scroll down a little if I can, dh by dt is simply equal to minus 5 centimeter cube per second divided by pi h square by 4, right? So this is great, because what we have now is an expression for how fast the water level is falling. So this is how fast the water level is falling at any given time, right? So this is the expression for that. But we are not interested in how fast it's falling at any given point of time. We're interested in the value of dh by dt at a very specific point of time. And that specific point of time is when the water level is 2.5 centimeters from the top, right? So what is the value of h? So let me just section out an area over here, just to do, because this is going to be a quick calculation. So what's the value of h when the water level is 2.5 centimeters from the top? Well, h is simply going to be equal to 10 centimeters minus 2.5 centimeters, right? So 2.5 centimeters is measured from the top, and h is measured from the bottom, and the height of the whole cone is 10 centimeters. So 10 centimeters minus 2.5 centimeters, well, that's what h is going to be. And so h at that point of time is going to be 7.5 centimeters. And so if we plug in the value of h in this expression for dH by dt, then what do we get? Well, we get dH by dt is equal to minus 5 centimeter cube per second divided by pi by 4 times 7.5 centimeters square, right? So which turns out to be, and you can do this using a calculator, this turns out to be minus 0.113 centimeters per second. So the water level, this is how fast the water level is falling when the water level is 2.5 centimeters from the top. So this is the value that we were looking for, and this is the answer to this particular question.